Here we have our internal resistance question. So we have this graph here for instead of a normal cell, it's a solar cell, but it makes no difference. The physics is identical. So the first thing is, how could we get these values from this graph? Well, if we just extend this line like so, then the equation that you're interested in is in the electricity section, and it's this one here. So the EMF is equal to IR plus I little r. Now that is the terminal PD V, so plus I times by little r. Just rearrange this equation a little bit to get V on one side, and we get V is equal to, move that bit over there, and we get plus minus I times by R, and we equate that to Y equals mx plus c. And if you look at this, then your y-intercept is there. What you're plotting on the y-axis is V. What you're plotting on the x-axis is I, which means that m is minus r. So you've got minus r left. So the y-intercept is the EMF, which is equal to 0.7, and the minus the gradient is equal to the internal resistance, little r. So little r is equal to minus, we just need to quickly work out the gradient here. That looks to me like, so when you change in y, which is 0.7, final value minus start value, so it's 0 minus 0.7 divided by, and the current here is, looks like final value of 87, it's either 86 or 87, I'm going to go 87 milliamps. Take away 0 times by 10 to the minus 3. So the minuses cancel each other out, and we get 0.7 divided by 87 exponent minus 3, which gives us R is equal to 8.045 ohms. Dot, dot, because I haven't rounded that. Okay, so you can get those two values off there. You must include that minus sign there. Now we're going to have a look at these two arrangements of various solar cells in order to try and get this delivered to this. So if we do figure 5 first, then we can simplify this to a 6 ohm resistor with an 8 ohm internal resistance cell with a 0.7 volt EMF like so. And I can do I is equal to V over R. Well, the EMF is 0.7. The total resistance of the circuit, including the internal resistance, is 14. And that is 50 milliamps, I think. So 0.7 divided by 14 is 50 milliamps. Just pressing there, 50 milliamps. So that's no good. So that's not enough. Now this rather strange arrangement here looks like this. We've still got our 6 ohm resistor there. We now have a parallel arrangement with an 8 ohm there and an 8 ohm there. Now because these are identical at 0.7 volts each, it's going to allow us to do a bit of simplification. 0.7 volts there as well. Here, the potential here and here are identical, which means that if I were to connect these with a wire, I know this is internally into the inside each of these cells. These are two things which are internally inside the cells. But for the circuit analysis point of view, if I start here and I go through this EMF and I go through this EMF, I'm always going to have the exact same potential here and here relative to anywhere else. So effectively, these two things are joined like that. With they can be considered to be joined with a little piece of wire there. So now we have two resistors in parallel, each of which has an 8 ohm value. So that means the total combined resistance of that is 4 ohms. So the total resistance is equal to 6 plus 4 plus 8, which gives you 18 ohms. That's just a trick there. You can guess that that would be the case, but analysing it otherwise is actually reasonably complicated. So we have the EMF. We've got these two in parallel, so they're going to be the same, so it's 0.7 plus this one 0.7, so that's 1.4 volts in total. So I is equal to V over R, 1.4 volts divided by 18 ohms this time. So 1.4 divided by 18 is 77.7 milliamps, so that's 78 milliamps, which is pretty close to the required 75. It is approximately equal to 75 milliamps. So the second circuit, figure 6, is okay. Right. Okay, 4.3. Right, so we've got some more information here. I think this pretty much ignores this part of the question now, and it's just a calculation entirely on its own. We need to work out the total intensity that we need to be able to generate this much power. So to start with, we want to use P equals IV, which can also be abbreviated to change to I squared R. We need to first of all work out the electrical power that needs to be delivered to the road sign, and to do that we're going to use this equation here, that the power is IV or I squared R, which would be more useful in this situation. So we're going to use these figures from here. We don't need any of this. Don't confuse it with this part here. So 75 times 10 to the minus 3 times all squared times by 6.0, and that will give us the amount of power that is delivered electrically. So 75 times 10 to the minus 3, square that, times by 6, and we get the electrical power is equal to 0.03375 watts. Now we need the solar power delivered. Well, the solar power delivered, if it's only 4% efficient, that's the electrical power delivered to the road sign. But this is the solar energy to useful electrical energy in the road sign. So it completely deals with all of the internal resistances and everything else. We don't need to worry about any of that. So the power of light, the solar power, then has to be, that is 4% of it, so we need to times that by 25 to get the solar power is equal to power E times by 100 divided by 4, which is times by 25. So that's 0.84375 watts. Okay, so that's the power delivered to the light. Now we need to work out the intensity. The intensity is equal to, well, you might not know what intensity is, but you can work it out from the units. It's power divided by area. So power divided by area. That's power, that's area. So we want this power, 0.84375, and we want this area, which is 32. We've got to be careful, that's in centimetres squared. This is in metres squared. So we need to convert centimetres squared to metres squared. And if you think this through, there are 100 centimetres in a metre. So we've got 100 there, we've got 100 there, which means we've got 10,000 centimetres squared in a metre squared. So it's times 10 to the minus 4 is the conversion factor there. So we need to divide that by 32 times 10 to the minus 4 gives us 263.67 dot dot dot, which rounds to 264, I think. Although that's actually, they're all in two significant figures, so we should probably do it to 260 to 2SF. For your information, the amount of sunlight incident upon the Earth is about 1 kilowatt per metre squared, so that seems a reasonable number to have as our answer. Question 5. So we got this standard ladder problem here, propped up against a wall. A very traditional problem. Explain how figure 7 shows that the friction between the ladder and the wall is negligible. Right, this force here is not the reaction force of the wall upon the ladder. You notice it says here it's the resultant force, so it's the reaction force added to any other frictional forces that are acting here, but it's acting at 90 degrees, so that's all reaction is the resultant. There's no extra friction added in there. So the resultant force of wall on ladder is at 90 degrees. If there were friction, this angle would change. So if you think about it, that's the reaction force. If there were a bit of friction acting up, for instance, that would be the resultant force, or vice versa if it was acting downwards. The forces acting on the ladder are in equilibrium. Draw an arrow on figure 7 to show the direction of the resultant force from the ground acting on the ladder. Right, well we've got this force acting on the ladder that way, we've got this force acting on the ladder that way, so we need a force acting on the ladder in that direction. So we don't know exactly what angle it will be, but it's going to start where they touch, like so, and it's going to go at some angle. The vertical theta, like so. Label your arrow G. There we go. The ladder is 8 meters long, weighs 390 newtons. Calculate the magnitude of the resultant force from the wall on the ladder. Okay. This is a standard approach. We don't know much about this force here, so we want to eliminate it. And to eliminate it, what we're going to do is we're going to take moments about this point here. So I'm going to label this point X, and we're going to take moments about X. Right, let's think of this now. So that's 8 meters. That is 390 newtons. And that is the force that we're trying to find out. That angle there is 30 degrees. That angle there is 60 degrees. So this distance here, we want this distance here, is 8 meters times by the cos of 30, using your trigonometry. This distance here, from here to where the weight is there, is going to be 4 meters. That's the length of that ladder there, because it's a uniform ladder, times by the sine of 30 degrees. Right, so we take the moments. We have F times by 8 cos 30 is equal to 390 times by 4 sine 30. So F is equal to 390 times by 4 divided by 8 times by sine 30 divided by cos 30, which 390 times by 4 divided by 8 times by sine of 30 divided by cos of 30. So that's 112 newtons, 50.58. So we'll do it to 2 sig figs. So that's 110 newtons to 2 SF. Right, now what happens as a person climbs this ladder? So as soon as they step on, the force on, there's an extra weight acting down, so the force on the ground acting upwards is going to increase. That's also going to increase the clockwise moment around this point here, which means that this resultant force is going to increase as well. So let's write that down. As they step on the ladder, the total, this is actually suggest changes and I'm sort of explaining it here, but I don't think that matters. The total clockwise moment will increase, so the resultant force at the wall increases and the force G increases. Okay, as they climb the ladder, what's going to happen? Well, their weight's going to move up here, which is going to continue to increase that moment, which means that both of these forces are going to increase as well. As they climb, the resultant at the top continues to increase, as does G. Okay, now as they climb, if this resultant force increases like this, then this means that G has to have a greater frictional force acting towards the right as well. So the friction at X pointing right also increases as they climb. So the angle of G to the vertical, so what I've labelled theta there, increases. Okay, so everything increases. Right, question 6. We've got this blurb here which you need to read, but essentially this trolley's going down with a heavier weight than this one, so they keep going backwards and forwards as you put more weight on the top and it moves the trolley down. Now there are 3 forces acting on this trolley here. We've got its weight acting down there, we've got the tension acting there, and we've got the normal reaction acting that way there. But in this question it asks us just for the ones parallel to the slope. So the first one that we need to draw on there is the tension, that's going to be acting up there. The second one is the component of the weight, which is acting parallel to the slope. So from your trigonometry, that's 35 degrees there, so that is sine of 35, and it's mg, but what's the mass of this trolley? It's a big M plus 2 little m's, so a big M plus 2 little m's times by g sine 35 gives you that. Right, assume we've got no friction on the pulley, air resistance is negligible. Show that the acceleration of any of the trolleys is this, because they'll both have the exact same acceleration because they're both attached to one another. Right, the tension here is going to be the same as the tension of the string here, same as tension on the other side of the pulley, it's frictionless, same as the tension here. So all the tensions cancel each other out. This one's being pulled up and this one's being pulled up by the exact same force. So they're going to cancel each other out. The forces that are pulling them down the slope, on the other hand, are going to differ, because this one is going to be m plus 2m times by g times by sine of 35, and this one is going to just be big M times by g times by sine of 35. So we're going to use Newton's second law, F equals ma, A equals F over m, and the resultant force there is the difference between these two forces here. So the acceleration is equal to the resultant force divided by the mass here. Now what I'm going to do is I'm going to stretch this out and just, there's the pulley. I want you to imagine that this whole thing is just stretched out in a big long line. And this, we've got a big force here, and we've got a force here. This force is this one, so that's mg sine 35, and this force is this one, m plus 2 little m's g sine 35. Okay, so those are my two forces acting on the ends. All of these are internal forces, and they all cancel each other out. This has a mass of m, this has a mass of m plus 2m. So what we can do is we can work out the resultant force as this one take away this one. So the resultant force is just equal to m plus 2m times pi g sine 35, take away mg sine 35. And then we need to divide that by the mass of the system. The string is light, so we can ignore that. So we need to add in all the masses. So we've got 2 little m's plus m for this one, and we've got plus another m for this one. So that's just equal to 2m's plus 2 big M's. Right, simplify this. That cancels with that, because when you multiply that and that bit, they're the same as that. So we get 2 little m g sine 35 divided by 2 big M and 2 little m added together. The 2's cancel, and we get mg sine 35 divided by, 2's cancel all the way through, can't just cancel one of them, big M plus little m, which is the same as that. Compare the momentum of trolley A and trolley B. Oh, this is dead easy. So A has a greater momentum as it has a greater mass, but they've got to have the same speed because they're connected. But the same speed as B because it's connected, they've got the same speed. P is equal to mv, remember. The last thing about momentum is, of course, momentum is a vector, so A's momentum will be in the opposite direction to B. So A momentum is in the opposite direction to B's. So that's comparing its vector size and magnitude. There we go. Okay, now we're going to move on to part 4, where we have this friction brake which reduces the acceleration to 25% of its maximum. And we've got a bunch of values here. We need to work out the time. So let's do that. So the real acceleration is going to equal to m times by g sine 35 divided by m plus little m, all times by 0.25 because of that there. We need a SUVAT equation. So SUVAT, we've got 9.0 meters there. That's going to be 0. That's going to be, oh, we don't care. Acceleration is that big expression there, and that's what we're trying to find. That's what we're trying to find out. So that's A real. I haven't left myself very much space there. That was silly. So we need to use S equals UT plus a half AT squared. I'm going to rearrange that to get T, and we get T is equal to the square root of 2S over A, because that is 0. So I'm going to work out what this fraction first is. So we have the mass of the concrete block 30 times by 9.81 times by sine of 35. So that's that bit, divided by 2 masses added together. So that's the acceleration, the maximum acceleration, this one, times it by 0.25 to find out the reduced acceleration. So that's 0.3376 meters per second squared. Now let's try this now. T is equal to the square root of 2 times by s, which is 9.0 from there, divided by 0.3375. Okay, so we want to do 18 divided by that answer there to get what's inside the square root the answer, and we get 7.301 seconds. So that's 7.3 seconds, which is quite fast. It takes 12 seconds to remove the blocks from the lower trolley and reload the upper trolley. Calculate the number of blocks you can transfer. So we've got total for 2 blocks, so that's the total time for 2 blocks. It's got to be the travel time of 7.3 seconds plus 12 seconds to switch them over at each end, which is of course 19.3 seconds. So then we've got trips is equal to the time in seconds divided by 19.3, 30 times by 60 divided by 19.3. So the number of trips is 93 trips. We have to lose the fraction, and then we times that by 2 to get the number of blocks. We times it by 2 to get 186 blocks. Okay, this is the resonance question. It's got quite a bit going on here, but actually each part breaks down relatively straightforwardly. So we've got spring A with a spring constant of that one's got spring constant of that, they've both got the same mass here. We need to deduce the spring constant of the mass in this example here. It gives us some values here. We're going to be using some of the stuff from simple harmonic motion. There are different ways of approaching this. The way I've done is use this one. So Vmax is equal to omega A, and we're also going to need this one here. So T is equal to 2 pi square root of m over k. And using those two equations we can sort out everything else. So from this one, if we want to find out what the maximum kinetic energy is, then the maximum kinetic energy is a half m Vmax squared, which is equal to a half times by m times by omega A. Omega is 2 pi f times by a all squared. So that bit there is that bit there, which I've squared, and then I've just times by a half m. So that is E max is equal to that. So now we just want to rearrange that to get m. So m is equal to E max divided by 2 pi fa squared times by 2 on the top. Now I can't see any way without working out mass first, but they seem to put that one at the bottom. It's a little bit confusing, but here we go. So 54 times 10 to the minus 3 joules divided by this fraction here, 2 times by pi times by f is 2.0 times by a, 2.5 sorry, times 10 to the minus 2. All of that is squared. So let's do that calculation. 54 times 10 to the minus 3 divided by 2 pi times by 2 times by 2.5 exponent minus 2 close bracket squared, and we get all of that, and I've forgotten the times 2 there. So that's 1.09426 ... kilograms. So that can go in here. All of these are to two significant figures. That's 1.1 to SF. Okay, now we're going to use this equation to work out what K is. So we need to flip the whole thing upside down to start with. Get F is equal to 1 over 2 pi square root of K over M. And then rearrange for K. So we get square root of K is equal to 2 pi F times by root M, square everything, K is equal to 2 pi F squared times by M. And we know all of this, so that's going to equal 2 times by pi times by 2 squared times by 1.09 ... Right, so we need to times that by 2 pi times by 2 squared, and we get 172.8, so that's equal to 172.8, which is equal to 170 to 2SF, which is what we have everything else to 2SF. Right, calculate the frequency of this one now. So up until this point, this spring has been irrelevant. Now we know the resonant frequency of one with K, so we just now need to do the resonant frequency of one with 3K. And from this equation here, we have, because F is equal to 1 over 2 pi times by root K over M, everything else stays the same, so the frequency is just proportional to the square root of K. So F B is equal to FA times by root of 3, because that's the extra amount there. So we've got 2 times by square root of 3 is equal to 3.464 hertz, or 3.5 hertz to 2 SF. Now this question you've got to be a little bit careful at because it's mixing things up. So this shows how the amplitude of oscillations of A varies. Now we're making two changes here. We're first of all repeating it with mass B, and we're also putting it in a beaker of oil. Okay, so mass B is going to look a bit like this. So that's B with no oil, and that's 3.464. That's B no oil. Now if you think about oil, oil's going to damp it, so what you're going to get is it's going to peak a little bit earlier than that, and it's going to go down like that. Okay, so that one is B with oil. So we just need to write two differences, but notice the question is explain it, so we've got to state what those differences are. So the first difference we can say, so we're not even comparing this one with this one, we're comparing this one with this one. So the resonant frequency is higher because B has a greater spring constant. Okay, so that value there, the resonant frequency there, is bigger than that value there because of that there. Second one we can say is that this gets wider due to the damping. So the peak is lower and wider due to the damping of the oil. But now the third one they have put on here, the amplitude would be lower at all frequencies due to energy losses from the system. Well, that's actually not true, that is, because we're comparing apples and oranges. We're comparing this B here with this A here. So the peak's probably going to be bigger at the resonant frequency of B than it was at the non-resonant frequency of A. We don't know. It might do. I think it will be. So that's not true. That's only true if you were comparing A with A's damped system, or you're comparing B with B's damped system. But they've tried to have it both ways. They're comparing that with that, and so that bit there in the mark scheme is just not true. So once again, well done AQA.